Okay, good. So the first thing we're going to go over is the creation of a dynamic array list in the C programming language. This is just a dynamic array list of ints, nothing fancy, right? It's just integers. And I don't have a remove method. The methods that I asked people to implement for the homework were a create method, a size method, a set method, a get method, an add method, and a delete method. So let's actually go over the creation process and what everything does. So I create my array list very simply with the create array list function. Effectively, when doing an object-oriented program like this in C, you're always passing the pointer to the object as the first thing into your quote-unquote method, which, again, these aren't really methods, but, like, yes, they are methods because our class and our private instance variables are stored inside of our struct here, which is storing all of our data. And then to mutate what's inside of our struct, we pass a mutable reference to our methods, which are just functions that take a pointer to the actual place that data is contained. And this is actually how C++ does object-oriented programming behind the scenes. When you write a method in C++, this keyword is a pointer to the current object passed as the first parameter behind the scenes, which is actually kind of cool to think about how this is exactly how C++ implements behind the scenes its object-oriented programming. In the same way that C is, you're basically implementing C OOP whenever you do C++ OOP, with the exception of some more advanced stuff like polymorphism, etc., which we're not going to talk about. Yes.
A question real quick about the kind of setup of struct. Can you kind of to like, if you wanted to focus more on like OOP, could you like use pointers to the, I guess, methods like in the struct itself?
Yes, you're 100% correct, and people do that.
Yeah, I saw an article saying like people did that before C++ existed.
The issue with doing that is you're still not able to actually directly access objects. So the only reason you would have a pointer to a function in here, so say I wanted my create array list pointer in here, so I'd have this be like p create array list, and then I would have this be a void pointer to a function. And we didn't go over this, and we're probably not going to be going over this because pointers, we're going to go over this later this week, but effectively you can have pointers to functions because functions are literally just code in memory and therefore bytes in memory that you can reference. So void p create array list, and it takes an array list pointer as one of the parameters. So I'm just going to assign it right here and a size t. But then the issue with this is the fact that you don't actually have. Why are they yelling at me? This is legal. Function type is not allowed here. Yes, it is. What do you mean it's not allowed here? Did I put the pointer on the wrong side? Is it star? I think I might have put the pointer on the wrong side. There we go. Okay. So long story short, don't worry if you have no idea what this syntax means. This is just a function pointer. But for Matt Keeling, who's asking this question, the issue is even if we set this to the create array list function, we don't have access to size an array. We still have to pass in the array list as a pointer if we want access to the object. So it's unlike C++ in that way, but sometimes they'll have function pointers to everything they want to be considered as like a legal method for their thing. So that's, yeah, this does happen, and I think this is how I've heard a bit about, there's like a Linux library, I'm forgetting what it's called, but they have some, like, everything is prefixed with the letter G objects and stuff, and it's a C library that effectively adds quote-unquote OOP to C, but it's not, I think they still have to do it like this, because you can't have access to these inside of a function pointer there.
I guess the only thing I could think it being like pretty useful for is like kind of documentation of like what functions you have.
Yeah, exactly. But some people will argue that that's already, if you have good practice and you're splitting up header files the right way, people would say you're doing that already anyway.
That's
so
fair.
we're gonna do some, I think maybe I'll do a linked list example later for actually how to split things up, because we have to show how we're actually gonna split this stuff up. Anyway, so I looked over a few people's code, and most of your code looks pretty good and pretty similar to this. So basically, long story short, we're not going to spend too much time on this. It's already 8:11, and I'd like to try and move this one faster today. So we're just going to go over this very briefly. Create array list takes in your array list and your initial size, and it creates an array list with that much size, right? So effectively, list size we set to our initial size, and then we allocate a chunk of memory the size of the initial size. Obviously, malloc allocates bytes, right? So you have to pass a number of bytes, so we have to multiply by the size of an integer, right, when we do that allocation. So then of course, malloc doesn't have to be casted, but we're going to cast it to an int pointer. There's huge fight. The biggest fight in the C programming language. If you want to know what the biggest fight in the C programming language is, it's should I cast malloc? This is one of the highest rated questions on Stack Overflow. People have argued about whether or not to cast malloc for years and years. Some people say yes, some people say no. I personally will always cast malloc because it's nice to see what the type, like in this instance where I declare the array up here, I don't know by looking at this code if this is an int point. Like if I get rid of this, I can't see that this is an int pointer. I have to look somewhere else. It's nice just to be able to look at this line and be like, oh yes, I'm allocating an int pointer here. Obviously you could look at size of int, but still, I like to cast the result of malloc, but don't have to. Anyway, again, malloc allocates in bytes, size of int times the initial size, easy peasy. So we store the size in our array list type. So when I call to get the size of the array list, we literally just return the size. Then setting an element in an array list, very easy. List array index equals element, right? So we're literally just accessing the array via the subscript operator and setting the inputted element, right? So index is the element to change the element at, and element is the new thing that we are setting. Obviously, it doesn't return anything. It's void. We could add on some protections here if we wanted to be fancy, an if statement that checks to see if the index is in bounds. In that case, set would return an error code probably of if something was out of bounds or not, but I'm not that fancy. Let's see. No, I'm not doing bounds check. Let's see. So get, again, same sort of thing going on here. We literally are just returning the index of whatever we want from the array at that position, right? So list array is our big allocated chunk of integers, so it's our array of integers, and we're just getting the array at the index. Easy peasy. So let's see, then add here, this is probably the hardest one. I say hardest, but it's only 3 lines if you've done this correctly. All you have to do, all I'm doing here is using realloc being the function that takes a pointer to a chunk of memory and then resizes it and places it in so effectively what realloc does, I don't know if I explained this well enough last time. Time for the MS Paint diagram. Ah, yes, MS Paint. I love MS Paint. So you malloc your big chunk of memory, right? So the operating system owns this big block of memory that starts at some M. This is our pointer to the thing, right? So this is M. M is the address that our big block of memory starts at. When we run realloc on our big chunk of memory M here, so M being a pointer, if we realloc M, what realloc does is it actually frees this entire thing and then it returns a new pointer to a copy of, so let's actually put something in here. Let's put like 1, 2, 3, 4. And now say we want to put 5 in here, but there's not enough room to put 5 in here. Effectively, what's going on is, first things first, we allocate a new space with room for however many integers we want. So we're reallocating to size 5, and then it copies whatever is in the initial memory position. So 1, 2, 3, 4. And then we have this extra memory position right here that we've realloced to. This is at some new memory address N, which we're going to get a pointer to. Then it frees this, so M is no longer a valid pointer. And now you have a new pointer to a new region of memory with more space than you used to, and now you can successfully write your 5 here, effectively. So that's what we're doing with realloc behind the scenes. That's effectively how realloc is working behind the scenes. So what realloc is taking is that initial pointer to our array location. Then it's taking the new size of the block of memory we want. So obviously we've just increased the size by 1. So now we can say list.size times size of int, and that's the new number of integers. Would it not be better to calloc? I make the argument that no, it's not better to calloc because it feels more natural. So the way that so for those of you who don't remember what calloc does, calloc initializes the memory to 0 when you allocate it. I make the argument that you wouldn't do that because I would say it's the same thing as when you declare an integer and you say int I and you declare your int I. Do you say int I equals 0 every single time? You're wasting an instruction there. I mean, it's additional instructions for you to have execute. I make the argument that no, I don't really care what the initial thing inside of my array is because I'll be setting it myself anyway. So yes, you can call calloc. I prefer to malloc because malloc is faster because you don't have to rewrite every single memory address in the array every single time, right? So well, you can't really use calloc as a replacement for realloc, though. It's not feasible to use calloc as a realloc replacement. I don't think. Does calloc have a thing where you can do reallocation with calloc by passing a pointer? I wasn't. If there is, I wasn't aware that there was a version of calloc that did that. My understanding of calloc is it's an alternative to malloc, which zeroes out the memory. Just like appended memory. So let's look at the calloc documentation. Calloc. So my understanding of calloc is that calloc effectively, instead of doing the multiplication yourself, you pass in the size of the type and the number of things that you want in your array, right? And then, yeah, okay, so all it does, allocates memory for an array of num objects of size. So literally, this is just doing num times size behind the scenes, and then allocating everything inside of it to 0. So it sets all bytes, initial bytes in this chunk of memory when you calloc it to 0, which, I mean, do you really want to do this? I mean, you're wasting bytes every time you declare an integer in a normal program. You're not setting it equal to 0 every single time. It's kind of redundant. So no, I wouldn't calloc there. But so I think you have to realloc in this case. And it's an interesting point because how do you calloc initialize things to 0 after a realloc? I guess you would have to do something like this where then you actually set the elements over to 0. It's interesting. You could also use memset. There's a memset function in string.h, which we'll be going over, I think tomorrow is string day. I love strings. String day is, let's see. Yeah, tomorrow is strings and things. So we're going to go over the entirety of string.h tomorrow. A lot of fun functions in string.h. So that'll be enjoyable. I hope I've memset to avoid bad pointers. I actually haven't heard of using memset to avoid bad pointers. The only thing that I was using memset for was I wrote, just as a little fun exercise for this, I wrote a oh no, I was using memcopy for my generic array list. I wrote a generic array list for fun that uses void pointers, so you can put whatever type you want in here as long as you pass the type size in beforehand. But then this requires a ton of overhead where every time you actually use the array list, you have to cast whatever you're putting into a void pointer. And then you have to, whenever you access something, you have to cast it to a pointer and then dealloc that pointer. So you can see me doing like these insane things to get an element out of the generic array list. But it still is, it's generic, so you can put whatever you want in there. And I also did an implementation with defines, which we're actually going to be talking about today. Anyway, enough sidetracking. Back to the add method. So effectively, when we add an element to it, all we're doing is we're increasing the size by 1, then we're reallocating to a new pointer, copying all of this over, and then finally, we set the final element of the list, using the subscript here, list size -1 to the new element. I saw Max was doing some complicated thing, in his case, with I forget how you were doing it, Max. You were like pre-allocating a pointer or something. This is way easier, at least in my opinion. All right, and then finally, I'll look over everyone's. If you want me to look over and offer criticism about your thing, I've received a few submissions so far for this project, so I'm very happy that I received so many submissions. It's very exciting. Anyway, finally, delete array list. Very straightforward. You just have to free the malloc or realloced pointer. You always have to. So realloc will free whatever the original pointer was, but you always still have to free whatever the final realloced pointer was. So here we can see free list array. Very straightforward, right? So we're just freeing our dynamically allocated array that's a member variable of our array list, right? So I did see someone was doing double pointers on their create array list and delete array list. You don't need to do double pointers. Double pointers are, so you can do double pointers, and especially for a linked list, the double pointer can be helpful. But in our case, it's much easier just to have the array list literally live right here inside of whatever function you're using in the stack frame of whatever function you're using, rather than dynamically allocating the array list itself. It can be helpful for the initial node of a linked list, which I actually don't even implement it like that, but we'll talk about that potentially later. And I can give code reviews for everyone who's submitted stuff, so I'll look over stuff and offer pointers probably later on tonight when I look over everyone's code. Okay, so for my very basic test here, create the array list. I create it with 0 elements, then I add 10 elements to it. Each element, I just have it be I do a for loop, right? So I'm going through 10 elements here, and I add 0 through 9 to the array list, right? So using the add method. Then I set 3 to 6, I set element 7 to 5 just to test the set method. Then finally, I print everything out here using my get method, and I use my size method here for the loop. So I'm going up until the size, and while I'm less than the size, we get the next element of the list. And finally, at the end, unlike C++ and Java, because Java has the garbage collector and C++ has a special thing that
Java.
Oh, Tyler's here. So Java is nice because effectively Java has, well, nice in the meanest sense of the word, in that the garbage collector lets this pointer here dangle until the garbage collector comes along and yeets it. Whereas in C, the second we don't need it, we tell it exactly, then we tell the operating system, get rid of this immediately, and the memory is free for our program to use again, right? So Java is bad in that regard. In C++, when your class is done, when you're done with a class, it deallocates things using its destructor method, which is called on the function end, which means that you don't need to explicitly call the delete, but you put the delete in your destructor, and then it's implicitly called on the closing brace or when the function returns. So you don't actually need this fancy delete array list here. Anyway, so that's part 1. In the interest of time, I'm debating if I should go over the linked list. Sure, why not? Let's quickly go over the linked list. Linked list is relative. You know what? Actually, in the interest of time, let's not go over the linked list. If you want to reference your linked list implementation against my linked list implementation, it is on my GitHub, as well as all the generics are also on my GitHub. Feel free to add me on here. And actually, I'll just send the file that I have. Give me a sec. IEEE Winters 21 C series, and all right, I linked the repo in the chat. So I have project 1s and project 1 extras. I should have deleted the BST. I didn't actually do the BST. I was too lazy. I got started on it. I got the insert node method, and then I was like, you know what? I don't even want to do, because effectively, I don't think I really specified how to do the BST well enough. Like, if you look at what I was saying to do, effectively, the issue was that I said, binary tree in C with breadth first search and depth first search. The issue being that I didn't really specify how you were actually supposed to add nodes. So I had some whole node like path system worked out, and then I was like, wait, I didn't tell them to do this, so this is actually going to be terrible. There's no point in implementing either of these searches in a binary search tree because the search is that's the whole point. The search algorithm of a binary search tree is supposed to be super easy, right? Because you just go down the side and it's ordered, right? So you know where everything is. There's no point in doing depth first and breadth first on a binary search tree. So after that, I was like, you know what? I'm not going to do the binary tree because it wasn't, my bonus problem wasn't clear enough. If you did some kind of binary tree in C, great. You're more experienced than the rest of us and are probably a god at C already. So, all right. That's enough with what we've already done. Let's get on to some new material. Oh boy, so exciting. All right. All right, so first things first, let's cover preprocessor directives. So I'm gonna do that in Godbolt. Should I do that in Godbolt? No, you know what? Actually, there are some benefits to doing some of this in Godbolt. All right, let's do this in Godbolt. Give me a sec. Godbolt.org. My favorite. Okay. Oh, this is what I was working on with Tyler last night. Very nice. Let's see. Instead of 03, I'm going to put in -E right here. Okay. So, we are using GCC 11.2 as our compiler. And this means that there is a compiler flag called the -E flag. And what the -E flag does is it runs the C preprocessor before and then spits out the source file with the preprocessor directives already parsed, which means we can actually see the result of the preprocessor here in our output here, which would normally have assembly in it. Anyway, that probably doesn't make sense yet. I should probably actually explain what the preprocessor is. So we've actually already seen the preprocessor. All of our include statements, include, stdio.h, this is a preprocessor directive. Effectively, what preprocessor directives are special statements that are executed by the C preprocessor, which is a little program that runs before your program is actually compiled. So before any C code is compiled into machine code, any statement that begins with a hashtag here, called a preprocessor directive, is quote unquote executed, and we're able to do some fancy stuff with it. So the first type of statement that we have is obviously the include statement. And what the include statement does is it looks at the file in whatever your quote unquote include path is, and this file, stdio.h, is a C file that contains C code. And what happens is it copies any code inside of these brackets into the current file before whatever we're looking at is compiled. So as you can see here, I've only written my main function down here, but we already have all of this code over here. And the code over here on this side is literally the code inside of stdio.h that has been copied into our file. So if I scroll all the way down to the bottom, you're going to see that, oh, here's my main function that I've written. But everything above this is all of the code inside of stdio.h. So effectively, includes are very straightforward. All they do, it's just copy and paste. Copy and paste the contents of whatever file I'm looking at here into this file at this exact position. So if I write a function before this, and I have int f, and now I have some int f that returns like 5 or something here, and I scroll all the way up to the top of this file, we can see that f's here, then I have include here, and then now down at the bottom I have int main. Everything inside of this file, all the contents of this file, have been directly copied and pasted at line 8, effectively. So it's as if you literally went into stdio.h, control A, copy, or to select all, control C to copy, and then control V right here on this line and replace the entire thing with that entire chunk of code. So that's all an include statement does. So include statements, very useful because you're including code from something else. It's how it's how all libraries in C work. So the next statement that we're going to talk about in terms of preprocessor directives is the define directive. So this one is fun. So hashtag define, and then something, let's call it, so define name. So effectively what define does is it defines a preprocessor, I guess they call it them preprocessor tokens. I actually don't know what they call this, but name and then thing. So I'm going to put like int here. This can be any string of characters here. So effectively what this does is it's another text replacement feature. So anywhere that the program sees name, it replaces it with whatever that string of text there is. So as you can see here, I define name to be this garbage here. And then all that happens is I'll show off the EEE program once we go over define in full. But effectively, whatever name is here is replaced with this chunk of text right here. So you can see I have this right here. Now, what is this useful for? This is useful when you have something really long, like a really long piece of code that you don't want to have to write every single time. So let's say I'm very annoyed with hello world, writing out hello world every single time, and I have to write out hello world a gazillion times for some reason. I could define hello here, and it's always good practice to have your defines be all caps. And then I could define hello to be literally the statement printf %d, or not %d. I can literally just have this be hello world exclamation point \n, and say that for some reason I have to print out hello world a gazillion times. I can just put hello, 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 hello here. And you can see that effectively the output after the preprocessor has been run is that we have printf hello world, hello world, hello world, hello world, hello world here, right? So again, it's a text replacement feature. When you define something, it replaces whatever this all caps token is with whatever is after it. So you can see that you can get code to look really weird here because I have no semicolons here, but the semicolons are implicitly included in this line right here. So after the preprocessor runs, the semicolons are all already in here. So defines are very, very useful in this case. The other reason you might use defines is because you can actually have finer grained control with preprocessor if statements. So hashtag ifdef, meaning if defined, and then the name of a token, includes or excludes whatever code is between it and an hashtag and if statement based on whether or not this token is defined at all. So this right here is an empty define. So while we're not defining anything, hello to mean anything, we are defining hello as existing. And then we can check using ifdef if hello exists or not. And you can actually have stuff here. This still is true. Effectively, all that this means is, okay, so whatever I put in between this ifdef and this endif statement is basically included on the condition that hello is defined or if hello is not defined. And the most common use for doing something like this is you will see people define a debug token up here. So debug, and they'll say if debug is defined, then we're going to printf something. And so this can be debug message. And you'll see people chuck this like into the body of their main program. You'll see people do stuff like this. So effectively what this means is that if debug is defined, then we print the debug message. If debug isn't defined, so I can define that as something else, then the code isn't included in here. So you can see that by defining, so I can comment this out, not define, debug, what am I doing? If we define debug, then printf debug message happens. If it's not defined, then it doesn't happen. And the reason for this is because you might have a giant program and you don't actually want whatever this line is compiled into code at all. You don't want it to be an if statement. You don't want to just have an if statement and have it actually run the check every time if you're in debug mode. But you actually want this line to not even be compiled into your program in the event that you aren't doing a debug build and you're doing a production build or something like that. And that's what can make C really fast is if you have certain sections of code and like giant chunks of code that you only want in a testing build but don't want at all in a production build, you can wrap things in an ifdef statement and then define debug or undefined debug. So effectively, ifdef includes things conditionally and define. So the number one time that you're going to see this is to actually check platforms. So if you're on Windows, you'll see them define Win32, and then they'll do stuff like this, where they'll do hashtag ifdef Win32. I don't know why I'm holding shift there. Hashtag and if. What are they mad at? So they'll have things like this, and they'll say, okay, if Windows 32 is defined, then we're going to include some Windows include. Then they'll include windows.h, which is the main Windows source library. And they're saying, obviously, windows.h isn't actually on here, but it looks like, so Win32, I've defined Win32 myself. And then they'll do other stuff like this. Well, they'll say, oh, there's also, I should mention this. There's also else. And you can have, so if we're on Win32, we define windows.h. Otherwise, we define some other library that we're using. And this is how they do a lot of quote unquote cross-platform code. It's not real cross-platform code, but effectively, certain compilers will actually define these operating systems directives beforehand, so it's able to tell what system you're on. There's also C version directives, so you can actually include or exclude code based on what version of C you're compiling for, which is another cool feature. So if you're compiling for one version, you use directives, these ifdefs and not defs. Oh yeah, so the opposite of ifdef, should have mentioned this, is the hashtag ifndef, which stands for if not defined. So basically, in this case, I can say if Windows 32 not defined, and here's a fun preprocessor directive, the error directive. If you ever encounter an error directive, the compilation stops immediately and prints out whatever message this is. So effectively, they're actually in godbolt.com right now, printing out error as a literal error. So I'm saying if Windows 32 is not defined, then print out error, whatever this error is. So I'm going to say not on Windows. And when I highlight this to see what the error is, it literally says error, we're not on Windows right now. But if we are on Windows, so if the compiler has defined some include, not include, hashtag define Win32. So if this is defined, then this actually fails, because if not defined, but it is defined, then we are on Windows, and this if statement doesn't execute, and this error never gets hit. So one thing that I really like about VS Code in particular is VS Code actually lets you see code that's executing or not executing. So as you can see here, this gets like grayed out because they know that Win32 is defined, and then any code inside of these chunks gets basically just grayed out because it's like, okay, we're not actually working with this, and this isn't going to be compiled. So anything I put in here is not even looked at by the compiler. So I can put random garbage in here, and it doesn't care or identify it as an error because it never actually gets included for compilation. Anyway, let me get this out of here. Back to godbolt.com. So that's your if statements. The number one use of if statements is going to be used in something called an include guard later. So let's talk about very briefly use cases for if statements. I've just gone over 3 of them, but we'll do it again. So number one, use for if, or let's say from least popular use case to most popular use case. Number three is going to be the logging capabilities. Logging if statements in code. Or if directives. It's not statements, these are directives. Directives. So again, difference between a statement and a directive. Directives are preprocessor directives. They begin with a hashtag. Statements are C statements in the C programming language, whereas you don't really can count directives as part of the C programming language. Obviously, they're there, and it's the C preprocessor, but they're not really C statements, right? So you don't end these with a semicolon. Rather, you start with a hashtag and then a directive and then some parameters to the directive. So number three is going to be logging inside of functions and including code conditionally, including like blocks of code conditionally, if directives in code. The second use case is going to be platform dependent code. So platform dependent code. And the number one use case is going to be include guards on header files. GUARDs on header files. Okay, so that is the directives that we really care about. So I did ifndef. The only other directive that we should care about is the hashtag undefined statement. So hashtag undefined, or is it undef? Actually, I've rarely used this. I guess it's undef. So all undefined does is then removes this from being defined. So if I say define win32 as, actually, it's probably easier to demonstrate this like closer to the actual body in main. So I'm gonna get rid of all of this. Effectively, so we define win32 here, then let's actually do something even better. Let's define meme as, let's have it just be printf. Hello, or actually, better yet, meme. So we define the word meme as meaning printf meme. So if I just put a bunch of memes here, we can see that it printfs meme. But now if I run hashtag undefined meme, so I put a directive here, undef meme, what this is effectively doing is removing the meaning of meme as a defined statement. So as we can see, while meme is defined, meme gets replaced with printf meme. But the second we undefine meme, meme goes back to being a meaningless word and just gets included right in the raw C source code. And obviously this now throws a compiler error because meme isn't actually a C thing, right? So it doesn't mean anything, right? So undefined gets rid of a definition if it's a null definition that doesn't mean anything like this. So meme doesn't mean anything. As you can see, since it doesn't mean anything, meme doesn't evaluate to anything. It's just empty. And then once we undefine it, though, now it sees meme as just the word meme. And this also works for if statements, obviously. So if I define meme and I say if def hashtag if def meme, and then I put something in here like an error meme is defined, and then hashtag undef. Now we're going to see that we encounter this error because meme is defined. But now if I hashtag undef meme here, meme is no longer defined, and it compiles with no issues. So effectively, this error does not get hit because if defined, well, yes, we defined it, but then we undefined it right after. And obviously, this goes as the C preprocessor goes down the source file, things can be defined for certain chunks of the source file and undefined for others. So it's defined until it then hits an undef statement. But if I undefine it afterwards, if I undef meme down here, meme is still defined for this if statement here. Meme is defined up here, still defined right here, and then finally it's undefined before main. So there is define, undefined, and if statements and includes, or if, not statements, but preprocessor directives. So if directives. All right. So this is the C preprocessor. Kind of confusing. How is everyone feeling about the C preprocessor? I think I'll show off E and comply with Dan Yi's wishes. E GitHub. E. All right. So this is a famous GitHub repository called E. The entire thing is just about E. It's E in every programming language. We're going for E.C. So effectively what they do here is they define every single type of thing into, so I'm actually going to take this and put this in Godbolt right here. Effectively, this is the world's largest define abuse that I've ever seen. What they're actually doing, I'm going to get rid of that. What is going on here is, actually, what the heck are they doing? This is ridiculous. Okay. I'm very confused why they have this thing on this other line here, but sure. So what they're doing is, oh, because on exit isn't defined because I pulled the thing out. But that shouldn't, I go down and look at this. What are they doing? That's completely illegal. Does this actually compile? Are they actually having this compile? I don't see how they're having this compile. This looks like an incredibly illegal program. I almost want to run this now. I almost want to take this and run it. Return E brackets 0. But it's not. You're in a for loop. Yes, I get that. But they don't have 2 ending brackets? I have a feeling whoever wrote this didn't actually know what they were doing. This is, the C++ one makes more sense. I'm very confused as to why this is legal here. If we go to e.cpp, it actually probably makes more makes more sense. They actually use C out and have a huge while loop. Long story short, it's actually compile. They're not throwing the compilation error. So if you know what, I should, instead of complaining about this, I should have just execution only it. Oh, look at that, it actually works. I have no idea how this works. How is this legal code? All right, well now I'm postponing the workshop and we're figuring out why this is legal. Give me a second. Okay, if main, good, makes sense. Forced loop, okay. For loop bracket, that's illegal. I don't know why that compiles. Then return E, brackets 0. But there's no closing bracket. What? I'm beyond impressed that this compiles. I'm actually kind of suspecting that Godbolt is getting something wrong here. Because I don't see how otherwise. This clearly runs. The program runs here. But this is what is supposedly our output, but this doesn't, that's not valid C. Anyway, long story short, instead of complaining about this for a gazillion years, which I could sit here complaining about this for a gazillion years, effectively, they just define every single thing to be E at different lengths of E, and then have their entire program be E's. And this compiles, and apparently prints out E to infinity, which, shocking. I did not expect them to be able to have this work, but it does, and it's a very strange way of having this run. Anyway, let's see. So Dan Yee here in the comments says, I remember Phipps saying that if you ever encounter someone using define for dumb things, get that person fired or quit. Yes, do not overuse define. Use define. So there's a huge argument about whether it's best to use define or global constants. So this is actually an important distinction. So int main return 0. So there's 2 ways to have some global constant, right? So say we want the number pi to be a thing, right? So we want to be able to use pi in our code, and so let's printf. We want some float %f pi, right? So there's two ways to have pi. The first way to have pi is the global constant pi. Can you have a variable in a define? So when you say, can you have a variable in a define, that's where, so this is where things actually get funky. There's no such thing as a variable in a define. Defines are exclusively text replacement. You're probably bringing up define macros, which we're about to do next. Yes. But effectively, all define does is text replacement. All include does is text replacement. All any of these defines do, most of these preprocessor directives, the important ones, just replace text with other texts. So hashtag include and CLUDE. I don't know why I have so much trouble spelling include. All define. What are they doing? Oh yeah, because pi is undefined. Obviously, I want to be on -e. Oh, hang on. Give me what I want. Get out of here. -e. So effectively, all include does is replace this line with the contents of this file, and all define does is look for instances of its word throughout the file, anytime throughout the rest of the file that word exists, and replaces it with whatever it has been defined to be. And there is a more advanced version of this, which I'm going to go over momentarily. Anyway, I just want to make the brief distinction between global constants, which, so I could say const float pi equals 3.141, whereas there are also people who do hashtag define pi to be 3.141. So what's the difference between these two? So it's actually kind of like syntax versus semantics. This is a syntactic replacement, where this is a semantic replacement. So this is that pi actually is 3.14 and pi is a named location in memory that has 3.41 assigned to it, whereas this is saying every time I see pi in the file, replace it with 3.14, and I don't know why I put the block there. But so effectively, every time you see the text pi in this file, replace it with 3.14. You actually can't have both of these on at the same time, because as you can see now, it thinks that it should replace the variable name pi with 3.14 here. But effectively, the question is, well, which of these should I do? Should I have it be a global constant, where I define pi as 3.141, or should I have it be replaced text every single time? And this is very, very application dependent. Let's see, what is this? Does define know the type? No, so that's the thing. This is not type safe. So defines are not type safe because it is literally just text replacement. It doesn't know anything about this. It views 3.141 as a string of characters. It does not know anything about this string of characters. Any semantic information about this string of characters is lost. Whereas in this case, the compiler can throw warnings at you about, variables and memory locations, whereas this replaces pi with just the constant 3.141. So effectively, it's very application specific. Pi is actually a big one that people fight about, whether it should be a global constant or if it should be a defined macro. I believe the way that they have it in the C standard library is that pi is a global constant. Or no, I think it's actually a macro. Time to find this out. So if I go to this linked list program right here, and I hashtag include math.h, and now if I want to use pi down here in main, mpi is, so look at that. So pi is actually defined. So mpi is 3.1415 all the way out, right? And then mpi1, I guess they don't actually. So all of these are actually defined. So all of these C constants are done using hashtag define rather than as global constants. So this is actually pretty interesting when you actually scroll down the list. So none of these constants are actually constants. They're just defined statements to a number which is viewed and interpreted as a constant. So it's basically copying and pasting pi in every time you use pi in a C program, it's copying and pasting the definition of pi directly into your statement. There is no memory location at which pi is being stored, at least not really. Well, behind the scenes, yes, really, because if we actually undo this and look at what's going on behind the scenes, we do see pi actually does have a memory location down here. This is it being stored in long format, but effectively this is pi down here, being stored at some memory location for constants, which we're going to talk about later. Anyway, let's see, what else do we want to talk about today? Blah, blah, blah. Oh, yes, define macros. So this is the next big thing with defines. Defines are actually a lot more powerful than we've talked about so far. The most powerful thing about define is you can have defines with parameters effectively. So what's a good example of define with a parameter? Because you can do some funky stuff with defines with parameters. So the most common define with a parameter I think you see is the max define. So effectively, you'll see people define a max macro that takes in an A and a B, and then basically says, all right, I'm going to evaluate to whatever the higher thing is. So the way that they do that is, I think it's a conditional. Yeah, so they use a ternary here that basically has max A, B evaluate to the higher of whatever A and B is. So they say if A is greater than B, then return A, else return B. So effectively, this here is a macro that is able to compute the max of two numbers. Now, why would you want a macro that does this instead of a function that does this? Does anyone know off the top of their head why it would be better to have a macro here rather than a function? So if I actually type this out and I have int A equals 2 or 3 and int B equals 5, and then I want C to be the max, and then I have that be the max of A and B. Can anyone tell me why you might want to do this? No need for call instruction. While that is true, so that's a very good point. So you can see here that this actually evaluates clean into a expression here, and we don't actually need to do a call or anything, and you're not doing a call, which means you're not pushing the function, the stack pointer up. That is a good reason. The number one reason you'd want to do this, though, is that this is completely type independent. So effectively, A and B are literally just treated as chunks of text. So when it sees this, it literally says, okay, we're going to replace A with the letter A and B with the letter B. But the thing is, this statement is a type independent statement. So if I have floats here as well, and I have float A, float B, and float max, and I'll call it f max of, and I'm going to call this fa and fb, and I place these in here. Effectively, we can see what happens here is this is completely legal, but we're getting the benefits of the fact that this is type independent. This is a generic code up here. Effectively, this statement, the comparison between floating points and integers is actually a very different thing here. But if we wanted to do this in a function, we need a float max function as well that takes float A and float B instead of int A and int B. And then for every single type of integer comparison you could want to do, you can just do it with a statement that looks like this. But if you want to functionize that and put that into a function, well, you don't want to type this out every time you want the max. And you don't want to write functions for every single possible type combination that you can do the max with. But with this macro right here, you can do every single type of max for every single numeric type in one line, effectively. Generic code for all of this. So you're going to see things like max, min, anything like this where it's like you want type independent code and you don't want to have to write a function for every single type. This is absolutely the way to do it. And so you're almost always going to see that max is implemented as a macro here. And let's briefly talk about what define macros actually do. They literally say, I'm going to take, well, if you send a non-numeric type, then it evaluates to illegal code effectively. But the issue is this is almost always going to be a legal statement. So you can compare, so greater than and less than. I mean, think about comparing pointers. If you pass in const char pointer, this will evaluate and compare pointers, as in like memory locations, and then return the higher memory location. So yes, this would be, if you use max on some fancy pointers, right? So if I do something along the lines of const char pointer d equals hello, and then I do const char pointer. Since we haven't done strings yet, but for everyone here, I think everyone here knows C strings or const char pointers. I'm gonna do C1 and C2, and then I have this be bellow. And then I do const char pointer max C equals the max of C1 and C2. This is legal code, but think about what this actually means. We're not actually getting the max of these two strings semantically. All that's happening here is that this is a pointer comparison. So this is saying if C1 is a higher memory address than C2, return the higher memory address. So all this is doing is getting the max of the memory addresses of these two pointers, rather than actually comparing these strings together. But yeah, so I mean, in C, there's technically nothing as a non-numeric type. The non-numeric types aren't actually real. Everything in C is secretly a numeric type. Even strings are pointers, which are numbers, which have memory locations which contain numbers. So you could do something like this, though, where if I actually dereference these pointers here and I send the pointers, you can see that the dereference actually goes across everything in here. So it literally takes the token here, the string right here, and copies it into every instance of A and B in this expression. So effectively, C1 dereferenced, C2 dereferenced. This is actually going to compare here let's see. So this is returning a dereference pointer to a char. So this actually then returns a char. And effectively, what we're saying here now is, okay, this actually does the comparison that we're looking for, which is the semantic comparison, which is saying, is H greater than B, right? Because when we dereference this, this is going to be returning a pointer to the memory location at which this char is stored, and then it's going to be comparing the two characters to see which one is higher. These are obviously ASCII characters, and then returning the pointer to this. It's not returning the pointer to the string, but it's returning the greater character, which you could then use to actually get the string. So obviously, if you wanted to do this yourself, you would have to do dereference C1 greater than dereference C2, and then not dereference C1 and C2 to return the actual string that's higher. But this returns the higher character. So, I mean, you can do some interesting stuff with this, but I just want to show how the copying of the macros actually works. So you can basically pass parameters into macros, which are just copied across whatever A and B are. So it's literally text replacement. Again, all macros are is text replacement, but now we're replacing text within the macro itself. So max is replaced with this statement right here, and whatever is our first parameter is replaced with our first parameter. So all A's are replaced with C1s, all B's are then replaced with C2s in this statement, right? So this is fun. I like the defined macros are some of the most powerful things that you have access to. You can do some really, really funky stuff with this. So another cool thing that you can do in defined macros, there's actually special secret, super secret operators. And these are the most secret operators in the entire C programming language that you can work with here. The first operator you can work with is the stringizing operator, which is this hashtag symbol. So the stringizing operator converts whatever is after it into a string. So if I say, I'm going to call this string str string and then hashtag A. So effectively what this does is convert whatever you pass in as A to a string. So the easiest way to see this is if I literally say string hello world here, it will convert this into the string hello world. So the hashtag in front of a token converts it to a string, but only inside of the defined macro. You can't use this inline directly by saying hashtag hello world here. So if I did something like this doesn't convert hello world into a string. This just fails compilation. But if you have it in the define macro, this is an operator that can only be used inside of your macros. It converts whatever token, as in whatever list of characters you've passed in here, into a string and puts them inside of string marks. So effectively, I could do something like printf hello world here, and we are now literally printing hello world. I don't need the hashtag here. String hello world. So as you can see, even though this wouldn't be legal C code in like any case, right? So if I uncompile this, we can see though that this literally prints hello world. If I actually hashtag include IO stream, hashtag include IO stream, it's not stram. Not IO stream. What am I doing? stdio. stdio. My God, I can't type. I just got my COVID booster. I think it's messing with my brain here. Okay, here we go. All right, so hello world, and if we switch over to execution mode, we're going to see that this executes and prints out hello world. And obviously, this is really funky because this is not valid C code at all, but it is because we're doing string replacement with the preprocessor. So the next thing, the other secret operator I want to talk about is the token concatenation operator. And this is probably my favorite operator in the entire language. This takes different things and converts them into a single unified token. So I'm going to take in some A and some B, and then I'm going to combine them with the token concatenation operator, which is hashtag. And you put one token on that side and the other token on that side. And effectively, this lets me combine things into other things. So a good example of this is combine things into other things. Yes, I know. Great talk. But effectively, so a good example of this is if I have A and B, and let me actually E on this. This concatenation, and I don't want include stdio because that's going to make this really long. It literally turns them into one combined token AB. So concat AB turns into the token AB. But something that's more fun about this is I can do something like this. I can say printf, or I can do prin, PRIN, and then TF as a secondary token. And then this combines into printf, and now I can call this as a function, as if it was a function. So printf, and then while I'm at it, why not also use stringify for the hell of it? String, I'll just call it string, taken in A, and then turn whatever A is into a string, hashtag, even more fun, just call it S. There you go. So this printf's hello world. I concat prin and tf into printf, and then that evaluates to printf. And then over here, I convert hello world into a string. And yes, this does look like a crime. In fact, you should never do anything like this. And if you see people at your company doing stuff like this, you should run. Run very fast, because this is not very good. But it's cool to know that you can do stuff like this. And there are many, many practical applications of this. So in my case, I'll show off a very brief practical application of this in my generic array list that I wrote. So I wrote a generic array list using defines up here. So I actually have the token concatenation. This is a token concatenation indirection. Don't ask me why I need indirection. Then I have token concatenation call, token concatenation indirection. And then I do this whole fancy type name thing where basically when I do this in my generic arraylist.c, I define the word type right here. And then I include my generic array list. And effectively, I define my type to be whatever type I actually want to use for my array list. And then in the actual H file where I'm actually defining all of the code, what ends up happening is the type of the array list and like the elements being contained in the array list are based on whatever the type has been defined to be. So if the type isn't defined, I actually throw an error down here that the type hasn't been specified using the hashtag else and then endif here. Then I undef the type afterwards. But long story short, the big important thing here is that I can actually then have the type name for all of these functions created using the actual type name. So effectively, I do void typed name, create array list with underscore and then the type name. And then this basically it concatenates type name with whatever the type is. So now when I actually go to use my array list here, all I have to do is say array list underscore and then the type name that I want for it. And as long as I've hashtag defined the name and then included this header, I can then use this with whatever type as long as it has the underscore for that type after it. So that's how you would do like a generic array list using define. So I can basically use all of this fancy stuff, all of these defines and preprocessor macros to create a completely generic array list that lets me put in whatever type I want for the array here, and then access all of my functions using the type in the function name, because I'm dynamically generating the function names based off of what type I input. So this is a pretty advanced use of type defs, and not even type defs. We're just doing defines here. But yeah, this is pretty fancy stuff. I do love a good define hack, and there's quite a few define hacks that you can use once you've mastered define macros. Anyway, enough about defines because we are coming up on 9:12, and I want to see what else I have to get to. So does anyone have any questions about macros and the C preprocessor? I guess I'm going to demonstrate an include guard later on. So that'll be fun. Let's see. All right. So the next thing I wanted to talk about was, if you have any questions, you can either speak up or type them in the chat, but I'll move on. And if anyone types anything, I'll answer that while I'm moving on. Anyway, so program structuring. So this is big because as up till right now, we've been implementing everything in one C file. Okay, so that's bad practice. You should never implement everything in one C file. We're going to implement things in the correct way, where we're going to use header files and forward declarations in those header files, and then implementation C files. So to talk about how a program should be structured in C, I have to bring up how we actually compile stuff, because that's what actually why we structure things the way that we do structure things. So why don't I actually first talk about C compilation and how C compilation actually works. And I'm going to pull up the C compilation pages. Okay, I want not any of this fancy stuff. Java point, cringe. Why are they talking about this? I want CPP reference. They are the only. All right, translation phases, blah, 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 blah. All right, this is actually way more complicated than what I actually cared about. And I think this is the C++ translation phases, which are similar but different. All right, so effectively, when your program goes to get compiled, the first thing that's going to happen, we don't actually care about this. We're going to start with preprocessor declarations. Blah, blah, blah. Where's preprocessor? Okay. The preprocessor doesn't get executed until stage 4, because keep in mind, they have to get rid of comments and stuff first, and whitespace. So whitespace and comments are all eliminated first. That's the first thing that happens before the preprocessor is even ran. I don't even know what's up here. Okay, so backslashes, for those of you who don't know, you can use backslashes in C to continue a line. So, for example, you could do something along the lines of return backslash and then 0 And effectively, I think it has to be at the beginning of the thing, or does it have to be directly on the end of the line? Okay, yeah, that's what's going on here. So effectively, if you do a backslash at the end of a line, and then you have your guy right here, they're going to, I guess you really can't even have a space there, huh? Okay. Anyway, as you can see here, in some cases like this, return and then \0, it's going to eliminate effectively the line break and place this 0 on the same line as this return if you put a backslash. It eliminates the new line in the actual source here. So that's phase 2, is them eliminating backslashes with new lines, by eliminating the new lines and backslashes, blah, blah, blah. Okay, this is where they handle empty source files. Phase 1, individual bytes. All right, so this is like source conversion. And they check the source set. And trigraph sequence replacement. Oh, these are so fun. They actually deleted these in C++, but I love these. Effectively, back in the day, some computers didn't have support for stuff like this, like curly brackets. So you'd have to use less than % to represent a curly bracket. So these are called trigraphs, and they replace oh yeah, and there's also these ones over here, the fun ones, question mark, question mark. So they got rid of these, but you can see down here a funny example of them doing a trigraph C program. But effectively, the first stage is to replace trigraphs in here and analyze the source, basically, character set, which nowadays trigraphs, no one uses trigraphs. That's like a holdover from when C was first invented, and not all keyboards had all of the keys you needed. But all right, phase 2, them removing backslashes. Phase 3, getting rid of comments and white space. Phase 4, preprocessor execution. Pretty straightforward. This is like all just preparation stuff. We don't really care about that. What we actually care about is compilation and linking. So phase 7, all we really care about is phases 4 through 8, and I don't even really care about phase 6 right here. It's kind of a meme phase. What are these? Source characters. All right, we don't care about phase 5 or phase 6 either. All we really care about is phase 4, the preprocessor being run, and when that happens, obviously include. Oh yeah, so include files, when you do a hashtag include, it does it recursively. So when you hashtag include, then phase 1 through 4 executes on all of your included files. So if your included files have includes, then it does this on all of their files as well. Anyway, long story short, what we really care about is the compilation phase and the linking phase. So let's briefly talk about what each of these do. Let's actually visualize this in our lovely .bolt.com. All right, so phase 1 through 4, we don't really care. Phase 4, we can visualize the output of phase 4 because it's copied all of the included files into our current source file, which is being compiled, right? So that is -E is the result after you've already run the preprocessor stage. The next thing is actually compiling this file into machine code. So to compile this file into machine code rather than an executable. So this is a very core distinction here. You can compile into either machine code or an executable. An executable is literally able to be run by your computer immediately, whereas machine code is literally just machine code that cannot be run immediately because it is missing some things. So this, you're probably wondering, what do I mean by missing some things? Well, there's actually quite a bit that something could be missing. The number one thing you're going to see in these, the C file here, the stdio.h, is that there's no code in this file. There's no code in this file at all. Everything in this file is declared extern in. So obviously, these are functions that are being declared. So we actually might even be able to find printf in here. Control F, printf. So effectively, here it is. So all your life, when you call printf in here, And when you start programming, you're normally told, oh, yeah, printf is defined in stdio.h, like that's why you're able to use printf. But now, when we look at what actually gets included in our source file, we see that printf is defined in here. There is a definition of printf, but there's no code for printf. It ends with a semicolon right here. Look at this. So where is printf coming from? And the answer to that is that printf has actually been pre-compiled by your system into raw machine code beforehand. And when you compile your program, what's actually going on behind the scenes is that it's linking your code of printf, when you call printf, to some pre-compiled machine code in some object file into a final executable. And that's the linking stage. That's the final stage of compilation. Once your file has been compiled into machine code and everyone else's files have some machine code implementation that may have been precompiled, then when you combine them together or link them together, then you can finally get a real executable. So a good example of this is actually what we are about to do, which I don't want to spoil this because I actually have the homework tonight is going to be you basically creating a array list. So you're going to be structuring your array list file correctly. But to demonstrate what I mean by correctly, I'm going to do it on my linked list instead. Okay? So I'm going to create effectively a few things here. So let me actually create a new folder here for, I'm gonna call it structured, or what's the date? This is what, homework? I guess this is technically homework 3, maybe homework 4 if you count the project as a homework. Okay, so I'm gonna call this homework 3. Sure, why not? And I'm gonna copy my linked list over because I like my linked list. Let's see, copy and paste. So I'm going to be giving this linked list a proper structure effectively. So you don't actually have to worry about what any of the code for the linked list does. All you have to know is, all right, yeah, I have these two structs right here, right? And I have all of these functions that do these things for my linked list, right? And then I have some piece of code main that's actually driving it, right? So effectively, this has everything inside one header in one file, right? So easy peasy, everything's in one file. Not bad, but not good. This isn't how we want to actually structure a C program, especially an enterprise C program. This would be considered terrible practice. What we want to do instead is to actually first define things the way that they've done it over here in the professional library, stdio.h. So what they're doing in stdio.h is they have what are called forward declarations. So we're actually going to create linked list.h right now. Linked list.h. And inside of linked list.h, we're going to do one thing. And the one thing that we are going to do is we're going to say, all right, everything from linked list that isn't code is going to go in our H file. So that might sound kind of confusing, but when I say not code, I mean not code. No algorithms, no function bodies, no implementations. This is all implementation code, whereas this is just type-defined code and function header code. So effectively, the first thing I'm going to do here is actually take our structs and put them in here. So effectively, the way that you can tell if something is code or not, if it's real code or not real code, is you take a look if it generates anything in Godbolt. So if I go to Compiler Explorer and I define a struct here and call it struct struct a, and then I put int a and b in here. So yeah, sure, I'll have some struct that contains some int a and int b, and then I'm going to return 0. We know that this struct isn't real code because I have to put the semicolon. We know that the struct isn't real code because it doesn't actually generate anything. Even if we declare this struct right here and I declare something of type A and then do a dot, or I shouldn't call it A, but whatever. A dot A equals 1 and A dot B equals 2 or something stupid like that, right? What are they mad about? Unknown type name A using the oh yeah. So I'm not type defing it. Okay. Anyway, you can see here that you can see what code has generated what lines. We know for a fact that this isn't actually real because this doesn't generate any lines of code. It's purely used by the compiler and us as humans to help us understand our code. But the compiler doesn't care. The compiler literally treats these as just two separate variables. So when I declare struct A right here, A, B, sure, they're being stored in memory in a specific location in a specific way specified by this struct, but all it sees is, okay, yeah, this line is us creating a variable A, and this line is us creating a variable B on the stack, and yeah, we have to order them in some specific way. But this right here itself just tells it that it has to do that. It doesn't tell it any actual thing to create. There's no lines of code, no actual instructions being created explicitly for this struct declaration. If there was, then you'd be getting into the territory of reflection, which we are not doing. Java has reflection. C does not technically have reflection as a paradigm. Anyway, so first things first, we are going to migrate our guy in here, and we're going to take everything that we need for our linked list, our libraries, into our... We're going to take libraries that we need for our types. So size T is actually not defined except in some of the standard libraries. So I'm going to try and get that by doing include. I'm actually going to use std int.h and see if they have it in there, because I think they do. Do they? No? Yes, they do. Okay. So std int.h has a bunch of int declarations, and I'm just using that to get size T in this file. All right, so next thing that we're going to do is we are going to take our function declarations, and we are going to copy these into our header file. So these are called forward declarations. All the forward declaration does is promise that somewhere out there these functions exist. And what this is good for is that now we can actually legally compile our program into an object file because we promise that functions with this signature. And when I say signature, all that actually has to have is the types. You actually don't even need the names of what these parameters are. For a signature, all you need is the return type, the name of the function, and the type and number of parameters. You do not actually need names for these parameters because you're not actually using them as parameters. All you're saying is, hey, a function named create list that returns nothing and takes a linked list pointer and a size T is going to exist in some file somewhere. And that's going to be in the implementation file, which we will get to after I didn't actually make any changes to that. I'm Xing out of all of this. Give me a second. All right. So create list, great. Size, I'll put the size in here. You might notice that I have a constant linked list pointer. I do this on purpose. This basically just signifies that size doesn't actually modify anything in linked list. Const is always good practice to use because effectively this prevents you from, when you write your function and you say, okay, I'm writing a function that gets the size of a linked list. In no circumstances should your size function modify any of the linked list's data. All size does is read from the linked list. So I say that linked list here is a const. So that way the compiler will yell at me if I try modifying linked list in the size function. And this is good practice because this prevents you from making stupid mistakes and modifying values where you shouldn't modify values. The difference between, famous saying, the difference between a good C programmer and a great C programmer is their ability to use const effectively and correctly. All right, so back to actually copying things over. We have our set method right here. I'm going to get our get method. I'm actually going to leave in the names in some of these because this is actually what's used for documentation when you actually look at things. So let's see, int linked list, delete linked list. Okay. And that is all of our linked list functions. So this is our linked list header file. So this contains a bunch of forward declarations for different linked list properties here, or not properties, for different linked list methods. So for the sake of demonstration. Sure, I'll get rid of the names of everything. Why not? Okay. So effectively now, we've encapsulated all of the linked lists functionality inside of a bunch of forward declarations. But we don't know how these things are actually being implemented. So now we actually have to do the implementation. And that's happening in this file right here. So inside of this file right here, I already have these structs up in the higher one. I'm going to run a hashtag include statement. So in the event that you're including a file that's inside of the same directory that you're working in, instead of including with these little brackets right here, and let me make this a bit bigger. I don't know if you guys can read. Instead of including with braces, you include with string marks, right? Double quotation marks. So I'm going to include linked list.h right here. And obviously, we're actually using stdlib and stdio inside of this implementation. So we include them here, but we don't have to include them here because at no point is our outwards facing implementation relying on stdlib and stdio.h. Only the implementation relies on these headers. We ourselves do not rely on this header, or on these headers for our user-facing implementation. Nowhere are we using printf inside of a header file. Nowhere are we using a type other than size t, which we're getting from stdin. All right, so next thing is we are including our header. So now, effectively, we have access to linked list because we've declared our structs in here. So we have access to that type in here, and no errors are being thrown here. In fact, I can open a terminal to actually look and see problems appear in real time if they do appear, which guess what, they won't because we're doing this right. Okay, so next thing I'm going to do is you're going to see we actually have our driver in here. You shouldn't have your driver in here. We're going to make a separate driver.c class, driver.c. So our driver code is actually going to be the thing that's going to be using our linked list. The entirety of the linked lists, basically implementation and header, are contained separately. Anything about the linked list is, did I name it wrong? I did name it wrong. I spelled driver wrong. I'm going to rename this. Thank you, Dan. driver. There you go. All right, so driver.c. Now, to actually use our linked list, I'm going to hashtag include linked list.h. Now, we're going to see something rather interesting here. And that is once this actually loads in. We're going to see that now this doesn't throw any errors. But notice something very fun here is the fact that linked list.h doesn't have any actual code in it. None of this actually has any code. Driver.c doesn't know anything about linked list.c. None of this is known to driver.c. So if we actually look at what's including what, and I pull up MS Paint here, we have two things. We have a few things here. So we have the header file, ll.c, linked list.ch, and that's being included directly in two things. That's being included in ll.c for our linked list implementation. So here's all of our actual code, and then we have our driver, so I'll call this d.c, which is including linked list.h. So effectively, we can actually look at driver.c and say, okay, so this method exists, create linked list exists and everything. The compiler doesn't care. We forward declared all of this in linked list.h. So the compiler says, all right, you've promised me that this exists somewhere. It better exist somewhere. But if I actually now try and compile this, I go to my terminal here, and I say, all right, I'd like to compile driver.c. Let's do it. GCC driver.c. We're going to have a driver. Where am I? I'm in the wrong folder, that's why. cd homework 3. Now I do GCC driver.c. We are going to get a fun error on, let's see, what are these errors here? Implicit declaration of function printf. Oh, because I'm not hashtag. Okay, so obviously I have a separate problem here, and that problem is that I use printf in the driver, but don't hashtag include stdio.h. Hashtag include stdio.h. Okay, so now, All right, so now you're going to see that the compiler just spit out a very, very strange, not strange error, but this doesn't look like a normal compiler error where it tells us code is wrong. Now what it's saying is undefined reference to all of these functions. And this is exactly what we expected. Effectively, this isn't a compiler error, this is actually a linker error. And you can see because it says it occurred in ld.exe, ld being the GCC linker. Effectively, what this says is, all right, so we were able to compile your code fine. Everything's right. You promised that these functions exist. But now the issue is, once it actually goes to make a .exe out of this, it says, hang on, you told me that there was going to be code somewhere for size, get, set, create linked list. But hey, there's not actually any code for this. And now it yells at you during the linker stage because it says, all right, you have all of these forward declarations here, and you promise these are going to exist, but they don't exist. So what do we do to actually get them to exist? Well, the answer is we compile our implementation, linkedlist.c here, into an object file, and then we compile our driver into an object file, and then we combine the two object files into a final exe. So instead of actually including this code directly in here, which we're not going to be doing, what we're going to be doing instead is converting this into machine code first into some ASM, so ll.o. And ll.o is literally just machine code for our linked list. Then we're going to be converting our driver into some object file, d.o. And then this has the actual code implementations for things that we promise exist in here. So when we link them together, then we can create our final exe, and it will say, oh, okay, I'm looking for these linked list implementation functions. I see that they're in here, and then they're going to basically be placed in the calls into the right spots, and we create our final d.exe like that. So I'll explain why we do this after I actually do it. So let's actually do it. So first things first is now I actually have to quickly look at this guy just to remember how I compile to a .o because I always rely on my makefile to do this for me. Let's see. It is I don't need this open, but I should save it before I X out of it. That's always a good idea. Let's see. I use the -C option? Yeah. CSX flags. Yeah, that's all garbage. Okay. So GCC uses the -C flag to say, hey, don't try turning me into an exe. I just want to be turned into machine code, not an exe. So I'm going to compile driver.c. And I'm going to specify an output file using -o and say convert driver.c into machine code driver.o. Okay, so this compilation statement right here says, okay, GCC compiler, don't convert me into an exe. That's what C says. Convert me into machine code. -o driver.o says the name of the output file is going to be driver.o, and the final parameter is the input, driver.c. So let's run it. And as you can see now, we have this binary file, driver.o. So this is actually machine code. This is raw machine code in here. So this is raw x86 machine code. Now we're going to convert our linked list implementation. Linked, that's capital. Linked list dot o is going to be our output, and our output is going to be linked list.c. Our input is going to be linked list.c. All right. So we convert our linked list into an O file, and now we can actually combine these using the linker. So if I do GCC, and now I provide both of these O files as an input, it'll just run the linker. So if I do linked list.o and driver.o, it's going to combine these into an exe. I'm going to have the output be driver.c. So again, the output name is just cosmetic. It doesn't actually have to be exe. So driver.exe, and I provide the list of object files to link together, and GCC now links them together. They're whining at me because main is still defined in linked list dot right here, isn't it? So, oh yeah, because I didn't save it. So let me so effectively they're saying, this is another thing that the linker will yell at you about, is if you have multiple functions defined, if you have a main function defined in your driver and your linked list.o, and then you try linking, it says, hey, you have two instances of this function, I don't know which one to use. So they're complaining because I accidentally left in, I think, my main in linked list.c. So now if I combine them, yeah, works flawlessly, and now I run driver.exe, and yeah, we can see that that's the correct output that I would have expected from my linked list test program. So effectively, you're probably thinking, oh, this seems like a whole hell of a lot of pain to go through, when I could just hashtag include the implementation itself inside of, if I could, why can't I just include my implementation and all of my, dots, my C code in linkedlist.h, and then I can avoid all of the pain of doing this fancy schmancy linking business. Why should I have to convert to these object files and then link the object files together? And there is a very, very good reason to do this, and its name is compile times. If you had to include giant C libraries every time instead of just header files, because think about how easy it is for the compiler to parse this right here. Okay, there's no code to go through. You're just making a promise that something's going to be taken care of later. But imagine you have to compile this every single time you hit the compile button. This code has to be compiled. But now you only have to compile linkedlist.c if you modify linkedlist.c. So effectively, if you're not changing your linked list.c, you're able to have this compiled once and then never worry about it until you edit it again. And it's just an object file, and you can link once every single time. And linking is obviously much faster than compiling. So it's much faster to have a separate C file and a H file, where the H file is just forward definitions, and then you just include the H file in your main driver. So I can talk actually rather extensively about the issues with header-only libraries. In fact, I have my own problems with compilation times. This project that I'm working on is a C++ project where I have a very fancy build system where I convert all of my... Make is very, very good at doing this, by the way. You might think, oh, that's such a pain, I have to type out the compilation every time. No, Make is explicitly designed. So I basically have this here. What this effectively reads is, anytime you edit a CPP file, it will just build that into an object file, which then gets included in the final link step right here. So it's very, very easy to automate this process. That's exactly what Make was designed to do, is basically automate this entire process of object files and linking. Anyway, the thing that I wanted to get to is, let's take a look really quick at how bad things actually are and why you would actually want to do something like this. So I have a, I have a function called, or a file called application.cpp. You can see I have quite a bit of includes here, okay? So I'm including a bunch of header files, the worst of which is this vkfw.hpp file. So if I go into this file right here by control clicking on it, this is going to open the library file, and this might take a second to load because this is miserable and a giant, giant file. But effectively, you're going to see the issue appear very, very, very quickly. Okay, so let's take a look. This is a 4,000 line file, and this header file does have code in it. You can clearly see there's code in here. Functions are being called, the whole 9 yards. This has to be compiled every single time, all 4,000 lines of this, every single time I compile my project, because there's code in here effectively. Also, you can see some fun examples of preprocessor if statements in here, where they're basically like, all right, if this fancy macro is here, then we include this entire code block. Otherwise, we don't. But long story short, all of this code, everything in this giant file, every time I compile my code, has to be compiled by the compiler. The compiler has to handle all of this. Now, here's the scary thing. This is nothing compared to something like Vulkan itself, where if I go find the Vulkan header, control click on the Vulkan header, I think that this is like 60,000 lines. Like, okay, no, this one's not that bad, actually, which is actually surprising. I was in a Vulkan header file the other day that's like 60,000 lines worth of code. Oh, yeah, because this is vulkan.hpp. What I want to see is the actual Vulkan header file. Give me Vulkan, Vulkan.h, not Vulkan.hpp. I know it's in here somewhere. I just have to find it. Vulkan HPP. I know you include Vulkan.h. All right, here it is. Okay, and then this includes all of these other different sub-Vulkan files. Is it Vulkan core? I'm trying to find the one that's like 10,000 lines, like over 100,000 lines long. This is what we're looking at. This one's 13,000. But okay, so think about this though for a second. All of this is included every single time. Every single time you do any kind of compilation, everything in here goes up the search tree like recursively. In fact, if you want to see a real horror story, there is actually a command called the H command, which solely prints out the number of header files you need. Okay, so I'm gonna show you the scariest thing of all time, which is probably I go to okay, so I'm gonna cd into my include. I have a master include file, and I'm gonna gcc -h master.hpp. What this command does is it prints out every single header file that you need for compilation. So, as you can see, just by including vulkan.h, every single one of these is a header file that has to be compiled every single time I run this program. As you can see, it's still going. So that's a lot of code right there. So when you get into real projects that use real libraries, which include ungodly amounts of header files, it's incredibly important that you don't compile any more code than you need to compile. You want to make sure you're compiling as little as possible, and splitting things up into headers is the perfect way to do that. So to end things off, almost 2 hours. What are you talking about, Dan? I'm right on time. 2 hours, we doing fine. Let me see. Where's my... All right, I covered compilation stages. Maybe I'll move this till tomorrow, because this requires talking about some kind of... I don't think I give a homework question on it, right? Yeah, my homework is for you to just restructure your Arraylist project. Yeah, you know what? I'll move running under the hood all of this. We're going to move this to as a discussion. We'll talk about it at the beginning of tomorrow. We kind of covered it, but like not enough. So this will be the things part of strings and things, where things will be running under the hood, which is actually talking about how things run in memory. The final thing I want to show you is why we need include guards, and include guards are pretty great. So terminal, once again, again, make sure when you do a real project that you use good practices, which are splitting up your quote unquote class, right? Your implementation, even if you're just using a completely, say you're not doing something that's like, all of this fancy structs and everything. Let's say you just have a bunch of functions. You should still have a .h file that just has all of the functions pre-declared in it, and then an actual implementation C file where you've split up the actual implementation into, and then you should compile them both to object files and link them together. So this is good structure. So let's talk briefly about what an include guard is and why you want an include guard. So let's say, for example, your project is more complicated than what we have here. This is a very basic, very, very basic project, but there can be a lot of issues that get run into when you start doing more advanced stuff. So I'm going to create another library for my project. I'm going to call this lib.h, and this is going to be some random library for my project that isn't actually going to do anything. All that it's going to do is, we know for a fact that so let's say that lib.h is, I don't know, it's going to have some function, some void function, do stuff. And our do stuff function is going to take a linked list and do something with a linked list. So linked list. And in order to work with that linked list, I have to hashtag include linked list here, right? So because I have a linked list parameter in here, I need to know that linked lists exist. So I include linked list. linklist.h. And now I'm able to use linked list, and it makes sense to use linked list in here, right? So do stuff. I'm going to take some linked list pointer and do something to this linked list. Maybe this is a print function. Anyway, this is some library. We're not actually going to implement the library. We're just going to forward declare a function in here that needs some kind of linked list, right? So, okay, now let's say that I want to use do stuff in my driver.c. So now to actually use do stuff in driver.c, I have to hashtag include lib.h. lib.h. Okay, so now we've immediately run into a problem here. So if I open up a new terminal, there is a problem, and what do you mean lib. What do you mean expected of file name? What's that supposed to mean? What does that mean? Linklist.h is a valid file in here. I have a feeling this is like lag, and it's not actually. I spelled include right? Did I spell it wrong in lib.h? Linked list.h? That's legal. Yes. Linked list.h. No issues in here. Lib.h is the actual name of it. Missing closing quote. I have a feeling that this is just lag. I'm going to reload this. F1, reload window. See if this fixes all of our issues. This should throw an error, just not the error that it's actually throwing. The error it should be throwing is that there's a redefinition issue, which there will be. And that's why we're going to need an include guard. Come on, yell at me. Yell at me. All right, you know what? To drive this point home, I'm actually just going to include it. And we will do a demo of including it. Terminal, you wanna work, Lamau? You wanna actually open up the terminal? Hello? I think my computer is dying. Let's take a look at these processor. What's going on? Discord. Discord's crashing my computer? Of course it is. Okay. Okay, there we go. That got it on its feet. All right. So this should be throwing an error. It's not throwing an error. It's whatever. We're going to compile it and prove that this does throw an error. So I'm going to say gcc driver.c, and we are immediately going to get a big fat, I'm not on the right folder, ct homework 3 gcc driver.c. Okay, all right, perfect. So we immediately get a bunch of errors, but we haven't done anything wrong. And this is going to be the big issue here, is redefinition of struct linked list. So we're going to get a ton of redefinition errors, because actually what's going on behind the scenes is we are including linked list.h twice. We're including it once here because we want to use linked list functions inside of this thing, and we want to use linked list functions or types inside of this library file right here. So when I include lib.h and linklist.h, what this is actually doing is text replacement. So if we actually copy the text ourselves, we can see that this lib.h expands effectively to this, and then linklist.h effectively expands to this. And now we have an issue, because now we have another include here which expands to the same exact thing. So as you can see, when we actually be the preprocessor ourselves and do out what the preprocessor has done, we see that we're literally including linked list, all of our definitions twice. And that is going to pose an issue. So the question is, how do we get around this? And the way that we get around this is with something called an include guard, which abuses the define macro that we were exploring before. So effectively, all an include guard is in the statement that says, is something defined? So we're going to create a macro that tells our library if it's defined or not. So our library is going to be linked list underscore, you see underscores a lot, h. So basically we're saying, all right, if this linked list underscore h is defined, then we are going to include this entire library, and you end the file with an end if. So we're going to include all of our statements in here if and only if linked list.h is defined. But we can see that linked list.h isn't defined. But if we're coming down here the first time, then, oh, so actually it's going to be ifndef. I don't know what I'm doing. Ifdef. So if not defined, so if our library has not been defined yet, then we're going to define our library. And once our library is defined, then we're going to define linkedlist.h to let future occurrences of linkedlist.h know that we've already been defined. So effectively, what's going on here? This is kind of jank, but I'll show you exactly. You'll also oftentimes see the define be directly under the check rather than at the end of the file. But let's actually take a look at what happens now. So first off, I'm just going to compile this. I don't know why does it keep closing my windows? So if I actually compile this, we're going to see that it actually, what are you doing? Come on. I don't know, why is it switching between my terminals? I want to be on this terminal. There we go. Okay, so we're going to see it compiles now, but it runs into the linker errors, but we're not messing around with the linker errors. All that actually matters is you can see that it's, compiling and would compile to an object file, right? So what we actually care about now, though, is taking a look at how this actually operates. So let's be the linker again. We're going to be the linker. We are the linker. So lib.h, we are going to replace ourselves, be the, not linker, the preprocessor, replace the text, okay? And now we're going to replace linkedlist.h with our instances of linked lists. So we copy this in, and we copy this in. And now let's take a look at what's actually going on here. It's saying if not defined linked list. Okay, linked list isn't defined right now. So we're going to define linked list and include all of our code. But now we're going to see on the second occurrence, if not defined, but linked list has been defined already because we defined it on the first inclusion. So now it's not included for a second time, and we can see that VS Code is very nice and grays this out for us to show us that this code inside of this if block hasn't been included, and hence we're only including it once. So that's what's known as an include guard, and you should put an include guard on every single library you have, because running into situations like this is actually much more common than you may think. Every single standard library has an include guard. So if I actually go into stdio.h, look, they have an include guard right here. If not defined, inc stdio.h, define stdio.h, and we're going to see at the very end here the end if for that include guard. So every single good, well-written library has an include guard on it, which prevents it from being included multiple times and causing redefinition errors. Otherwise, you're going to very quickly run into issues. I can actually probably dig through any of these libraries and see all of them have include guards. So include guards, very important for C libraries and good structuring. Your homework tonight is effectively, let's see. I want you first to do, oh, crap, I gave it away. So I'm going to have you do a max macro again. Okay. And then I'm going to have you write a macro that turns into a for loop. So because, let's see, variable name, size, and statement. Right. So for loops are one of the most popular things in the entire language. So I'm going to have you write a for generation macro where you put the variable name, then you put the size, and then you put the statement, and that's everything. So the size it goes up to, and this is basically just going to be an iteration macro. So effectively, I'll give an example here. For I to 10, and then printf, and I'm going to put the semicolon is going to go on the inside here because semicolons aren't required for text replacement macros. And I'm going to have you print out the number D, or %d, and then print out I as the d. So effectively, this prints out the numbers 1 through 10. So this would evaluate something like 4 int I equals 0, while I is less than 10, I plus plus, and then your statement. So this is just an example of what this might actually evaluate to. Okay, so that's your macro fun homework. Have fun with macros. And then part 2 of this is if you did project 1, to restructure your project one into, I don't know why I say 2 files. Do it into 3 files. 3, a driver that has your main function, Arraylist.c that has your implementation. Oh, okay. So, and then I say to write a header with all your forward declarations, the structs and the methods, called Arraylist.h, and you should have an include guard on your header file. And then your Arraylist.c should include your Arraylist.h. Your demo.c should only include Arraylist.h and not Arraylist.c. And then I want you to compile into object files and then link them together. I don't think you can do this on Compiler Explorer. I think you're going to have to install a real C compiler. Does anyone not have a real C compiler on their system? If you have, just out of curiosity, is anyone here like struggling and does not have a C compiler? Preferably GCC would be your C compiler, but if you use Clang instead, I can respect Clang. I've been reading up on Clang, has a lot of good features. All right, any questions about anything that was discussed today before we wrap things up? Anything?